Right, so the first one is what's the difference between a longitudinal and a progressive transverse? Longitudinal and transverse. Okay, so what did we go for the first one? Longitudinal. Anybody want to volunteer? Joshua, thanks for volunteering. What did you go for this one?
Travels.
What travels? Yeah? Yep, that's one way of doing it, yeah. So longitudinal is this one that's... No, that's longitudinal. Yeah, which is the one parallel. The transverse is the perpendicular one. What?
Oh, yeah.
Yeah. So longitudinal waves vibrate in a direction parallel to its motion, its movement. Yeah, and then we can also say the energy. What would we say? We would say this energy. Yeah. Oh, you're going to go say, oh yeah, replace vibration with energy transfer, yeah.
Not vibration, movement.
Oh yeah, because it's this energy, yeah. So you could replace movement with energy transfer if you want. And you can do it in terms of the source, yeah. So you said...
The direction of propagation is parallel to the vibration.
That's it, yeah. The propagation means movement, yeah. So yeah, there's many ways to put it. I think this is probably the simplest of all of them, but everybody's answer has been fine, so good job. And then transverse? Yes, actually, the only difference for transverse, etc., perpendicular, etc. And as you said, Daniel, you could also say that transverse waves, they vibrate in a direction, they propagate perpendicular to the disturbance of the source. And how you would replace movement with energy transfer. Okay, so you have some flexibility here. Right, part 2. Give an example of a longitudinal wave. Yep. And then for part 3 now, transverse? Yeah, I think ocean wave is the safest, because light can be both, but ocean wave is just longitudinal, transverse. Right, now part 4, 3 properties common to all electromagnetic waves. They're all transverse except when you make them longitudinal. So I was thinking about that too. We'll use that one as a last resort. Give me something else. We'll delay that one for a moment. Except for the ones that don't. That's true for all waves. Something special about electromagnetic waves. Except for the ones that have low frequency. What's that? Yes? Yeah, finally we have one. They all travel at the speed of light. So the radio waves, microwaves, light waves, gamma waves, they all, electromagnetic waves, have a velocity of c. So we can say the velocity equals c, which is the speed of light. And this is, I don't want to say it just yet, but what's the second point here? Yeah, that's it. They don't need a medium to travel in. They can travel in a vacuum, which is unique to electromagnetic waves. Travel in a vacuum. And this here is only true in a vacuum because they slow down through glass or whatever. But one more. Now, okay. I would prefer things unique to electromagnetic, but it doesn't have to be. But these are better. So give me something else that are common to all electromagnetic waves. So as a last resort, we can go with transverse.
The energy transfer is not matter.
What do you mean?
The form of energy transfer.
Yeah.
It's not in form of matter.
True, but that's the second point, really. Well, no, okay, I suppose we could make that another point. We can say they travel in a vacuum. Yeah, and the energy transfer is not a transfer of matter. But maybe we can get something else, though. This is kind of similar to the second point.
They're all visible.
Except for the ones that are invisible, so no. We'll go with transverse, except I need to at least add something to it. They're naturally transverse waves, but you can make them longitudinal by, what's the polarizing? Yeah. So we at least have to say they naturally occur as transverse waves. Naturally transverse. No, it's not naturally longitudinal waves. You polarize them to make them transverse. They're naturally longitudinal. They're naturally going out like this. We polarize them to make them the transverse. So naturally longitudinal. Okay, so that's 3, 4, 5, 6, 7 marks. There's not any calculations there, it's all just definitions. The part B is all calculations. So we'll do part B bit by bit. Yes?
Are you sure they're naturally longitudinal?
No. Well, Joshua, if you look here, I'm thinking about a radio wave. When you polarize something, look up. When you polarize something, what you do is you take your wave and you cut away all the pieces except for one slice that's vibrating up and down in a perpendicular direction. So what type of wave is this? Transverse. So this one here must be longitudinal. So I think electromagnetic waves occur naturally as longitudinal waves. Anybody strongly disagree? Or even mildly disagree? Go ahead.
Light and other types of electromagnetic radiation are transmitted.
Naturally, or? Alright. Let's deal with that by removing this one then. No, I'll just go with the last one, that the energy transfer, how much energy is transferred by the wave, is proportional to the frequency of the wave. Yes, actually, bizarrely. So it's unique to them. Because if you think about an ocean wave, Tal, the energy transfer would depend on the mass of the water, how fast the water is moving, and so on. But bizarrely, for electromagnetic, it only depends on the frequency of the light or wave. But I didn't want to say this one yet because we haven't done this one yet, okay? This one is actually going to be in the atoms section of the course. Yeah. So it's the frequency of the electromagnetic wave that determines the energy. So for example, what would be a high energy wave? What would be high energy? Like an X-ray. X-ray? Gamma. So these have high frequency. And what would be a low energy wave? Yeah. Lower than infrared even. Radio wave. So that would be low frequency. Okay, B part 1. Try B part 1 now, please. B part 1, it's 3 times 10 to the 5 lines per meter. So that means in 1 meter you have 3 times 10 to the 5 lines. So they want the distance between each line. So that's actually just D equals 1 meter divided by 3 times 10 to the 5. So D equals 0.333 times 10 to the minus 5. So D equals 33.3 times 10 to the minus 3 meters. So the distance, no, that's not right, sorry.
Minus,
I went to,
minus 7.
okay. If I multiply, I'll just multiply by 1. So if I multiply this by 10, this is minus 6, sorry. So the D is 3.33 micrometers. That's the distance between each line. Okay, try the second part. So the second part now is the light is shone through the grate and it diffracts. So there's 2 formulas for this one. The one with the sine theta in it and the one without the sine theta. And in fact you could use both here to get the answer. So try part 2 now, please. The second part now. So I will need this answer. So you've got 2 formulas here which are helpful. The first formula is lambda equals xs over d, and then the second formula, which is not actually in the formula book, it looks like, is n lambda equals s sine theta. What do you mean? But I'm sticking with S because that's what they use in the formula book for the slit distance.
Not the line? But you said S in this formula is line spacing.
Yes.
Yeah, but they use D.
Sorry. S is the slit separation. Which I know they use D in here, and in the formula I wrote in class I use D.
But in the formula book they use S.
Yes. So do you want me to use D or S?
I don't know.
I'll just use what's in the formula book.
Yeah, okay.
So what you have here is, I'll draw it here for you. So the S is the distance between the slits, and then it shines on the board, and you have a dot here. This is n equals 0. You have a dot here. This is n equals 1. You have a dot here. This is n equals 2. A dot here. This is n equals 1. A dot here. This is n equals 2.
What is D?
Which one? The small one or the... Oh, there's only one D. That one is the distance between the slits to the screen. So that's that there.
And if they use the small D, it's the same as S.
Yes.
And X?
And X is the distance between the dots. This is the X. Okay. And do we know anything else? Yeah, we're looking at the second dot here. And we know the lambda, the light, is 633 nanometers. So the question is, what is the angle? So really we have no choice, I guess. We have to use the second formula. So we can say theta equals sine inverse n lambda over s, which is sine inverse 2 times 633 times 10 to the minus 9 all over what did I have for my S? 3.33 times 10 to the minus 6. That can be cleaned up as sine inverse. That roughly goes in as about twice 4. I mean, I don't have a calculator, but it should be roughly equal to 4 times 10 to the minus 3. You should get something like this in radians. Ugh. What angle did you get in radians? Did you get something like 0.004 radians?
0.1.
0.4? Radians or degrees?
Radians.
Yeah, what are those radians? I'm just curious. Is it 0.00?
In radians.
In radians?
0.4. In degrees it's 22.
Oh, okay. I guess I can't do it in my head. So in degrees it's 22 degrees.
Yeah, 22.3.
Okay. 22.3 degrees. Yeah, that's fine. Okay. So the next part is, what is the highest order? So for the next part they want to know, what is the biggest n value you can have? The maximum n. So try that for me. Well, before you do, what's special about the biggest n value?
Sin theta equals 1.
Yeah, or what's the theta basically? 90. So as theta reaches 90, you reach the limit for the n. So in other words, put theta as 90 and see what you get for n. Let's have a look at it. So in this formula we are still using, so for part 3, n lambda equals f sine theta, but here the theta is 90. That's the maximum angle. So sine 90 is gone. So you have n equals s over lambda. This is 3.33 times 10 to the minus 6, and the lambda was 633 times 10 to the minus 9. So what does this come out as before you round it? Before you round it? 5.26. Well, it doesn't matter, because what do we use for n? The n is 5. That's the maximum n. You can't have 0.26 because the n goes 0, 1, 2, 3, 4, 5, and you never get anything after that, because you can't have 5.26 and n cannot equal 6, because then you're bigger than the 90. So yeah, 5 is the maximum order.
Do we use a calculator in degrees or radians?
For this part it doesn't matter.
Okay.
Oh, for the previous part, both answers are acceptable, but it's normal to give the answers degrees. Yeah, because 90 needs to be converted into pi over 2 then, if it's a radian. Okay, fine. Either is fine, but 90 degrees in radians is pi over 2. We're happy? I know I am. Right. Part 4, the last part, is quite difficult. So I'll give you a few minutes to try the last part. The English is a little bit complicated in it as well, so please read it carefully. So what they're saying here, in the previous question you had red light, and your red light the red light is replaced by blue light, and it's found that the diffraction angle for one order of red light coincides exactly with the diffraction angle for the blue light in the next order spectrum. So what's happening here is, here's the red light, and here's the red light hitting n equals 1 for the red light. And then they say the blue light, the diffraction angle for one order of the red light coincides, so that coincide means it's in the same place, as the diffraction angle for the blue light in the next order spectrum. English no makes sense. Let's try that again. The red light is replaced by blue light, and it is found that the diffraction angle for one order of the red light coincides exactly with the diffraction angle for the blue light in the next order spectrum. Yeah. I think, unfortunately, when they say the diffraction angle for one order of red light, I don't think they mean n equals 1. No, just n. Bad English. It doesn't feel like an EAP teacher wrote this one.
EAP teacher that just read one physics book.
Yeah.
Or visited one lesson.
Unfortunately, they use the word 1, but they don't mean the number 1 when they use it. I'm sure you know in English 1 can also mean like general. So yeah, that's n, and then the blue light. The blue light in the same place will be an n plus 1. Now the good thing is, you know the wavelength for the red light is 633 nanometers, and the wavelength for the blue light is 506.4 nanometers. They want to know what the n plus 1 is. So what formula could I use? I could use, is it the sine one again? Okay. So I have n lambda equals s sine theta. This can be for the red. And then for the blue, I have n plus 1 lambda. And this is a different lambda. But what's good here is the s is the same diffraction gradient, and the theta is the same. So you get n lambda 1 equals n plus 1 lambda 2. So n lambda 1 equals n lambda 2 plus lambda 2. So you have n lambda 1 minus lambda 2 equals lambda 2. So you get n equals lambda 2 over lambda 1 minus lambda 2. So what's the wavelength for the blue? 506.4 nanometers minus 506.4 nanometers. And for the red, 633 nanometers. All those nanometers cancel. So what do you get here, please? Exactly. Amazing. So what's the n plus 1? 5. So you're going to tell the second part is much easier than the first part. What is the theta now? So let's just use this formula here. So you have n lambda 1 equals s sine theta. So theta equals n lambda 1, sine inverse n lambda 1 over s, which is sine inverse 4 times 633 times 10 to the minus 9 all over 3.33 times 10 to the minus 6. What do we get here? 49.5 degrees. Yeah? Get the same answer? Yes? Great. Okay, good.